So let me go ahead and introduce Bradd very quickly. Rather, I should say I should let Bradd introduce himself. But just as a preamble to that, Bradd and I work very closely together at RethinkX. Bradd does the overwhelming lion's share of the systems dynamics modeling that informs the general behavior within our models and our analyses. So his work is crucial. We use the Stella software environment, and Bradd can talk to you about his deep expertise and in Stella and where that comes from. And what I'm hoping from this session is that Bradd will be able to give us a sense, a taste of how rich and deep the history of disruptions runs. It's really extraordinary, and Bradd has done incredible research over the last. He's basically done COVID-inspired and driven research since the COVID pandemic began. Bradd has been amassing an extraordinary compendium of examples of disruption throughout history. And I'm hoping that we'll get to hear about just a tiny little bit of a tiny little sampling of some of those today. But stay tuned, because at some point in the not too distant future, this content will be appearing fully formed in books and hopefully some other media as well. So you guys are getting a very tantalizing preview of some really fun stuff that's going to come over the next year or so from our organization. So with that, let me turn it over to Bradd and thank him for joining us. It's 2 a.m. in Norway, where he is. So thanks for making the time at this unpleasant hour, Bradd. And please introduce yourself and tell us a little bit about your background before you get into the session, if you would.
Okay, sure. My name is Bradd Libby, and I work with Adam. So I'm a research fellow at RethinkX. And if anyone can't hear me or anything, or if my voice is breaking up or something's confusing, please just chime in and let me know. But my background is I have a doctorate degree in chemical engineering. I'm from the U.S. originally, but moved to Norway about 10 years ago, and have done a variety of sort of engineering type jobs. I worked for a couple of years as an Arctic researcher, physically making equipment that we put onto ships that would go to the Arctic. So electronics with code running it. But I also have a background in computer simulation, system dynamics, systems thinking. So basically, ordinary differential equations and lookup tables, essentially. For complex systems, economic interaction of sort of economics and social factors and technology, and I was doing that and saw the the work that RethinkX was doing, that Adam and Tony Seba and James Arbib were doing together, and was really impressed by it. So I started with RethinkX 4 years ago now, so November 2017. So I do, the analysis, RethinkX's analysis is very much driven by the cost of technology, the performance and capabilities of technology going up over time, the cost coming down over time, and that creating conditions where, one technology might quickly replace another one, things that we're seeing now with things like solar panels and lithium-ion batteries. So, can everybody hear me? I don't know. I just heard some sort of.
Yeah.
I barely ever use Discord or Roblox.
There'll be a kind of little ba-doop noise in the background when people join the channel or leave the channel. So one can just ignore those.
That's what I figured that was.
Yeah, but I can hear you perfectly. Yeah.
Okay, so if you've ever seen any of the presentations by Tony Seba, he starts out some of them talking about the history of cars, the history of transportation. He shows off a photograph of New York City in the year 1900, and it's full of horse-drawn wagons. And he shows off a photograph the same day of the year. It's Easter Day in 1913, so 13 years later, and the streets is just full of cars, and there's only one horse-drawn wagon in a sea of cars. He said, this is how quickly technologies change, and we've seen this in our own lives too. So mobile phones came, and people stopped using landline phones, and then the smartphone, the iPhone came, and people stopped using their flip phones. And it's not just they stopped using their flip phones; they also stopped using their digital cameras, because iPhones have digital cameras on them. And the iPhone came out 2007, so 14 years ago. And it just seems like, how did we do anything before that? How did people used to drive around and get lost and didn't have access to driving directions or whatever. Now you can stream. People used to have DVDs or CDs and cassette tapes and 8-tracks and vinyl. So these technologies come along and wipe each other out, and it got me thinking. And this is just something I sort of worked on as a project and side hobby was for a while, and now the last year or so. So basically, my COVID project has been sort of really doing a deep dive into all of the technologies that I can think of, and how they sort of interact with each other. So the car, it was a disruption over a 13-year period or so, 15-year period. It replaced horses for transportation. But the car has other parts to it. You need steel, there's pneumatic tires, there's glass, there's the internal combustion engine. And each of those things have been sort of disruptive in their own rights. So the internal combustion engine is used to move cars and trucks, but it's also used just to generate electricity. Big diesel generators are used to make electricity, and that kicked off all sorts of other disruptive ways of changing technologies, going from candles and coal gas to electric lighting. The electric generator was also a key technology for making radio possible. So if you can't generate a very large electric current, you can make a radio signal, and it's like a parlor trick. You can make a bell ring on the other side of the room. But if you have a really powerful radio transmitter, you can send a signal across an ocean, across to the other side of the world, and you can hear somebody's voice even if they're on the other side of the world. And radio waves become the basis of television. Radio waves are the basis of Wi-Fi. So I'm using radio waves right now to communicate, to send my voice to you on the other side of the world. So and it got me thinking, how far back in history does this go? How what kinds of conditions do we see rapid changes occur like this? And it seems like the more I've looked into it, the more examples that I find, and not just individually, but like I said, they're all interconnected. Of the internal combustion engine gives rise to the car, but it also gives rise to radio transmissions, which give rise to TV, which gives rise to Wi-Fi, which is a key part of your iPhone, which itself was disruptive to landline phones and to digital cameras, and digital cameras were quickly replaced film cameras. And I see this same sort of pattern over and over again, this sort of pattern of disruption, where a new technology comes along, it gets cheaper over time in a very predictable pattern, a pattern called Wright's law, which is essentially the cumulative number of objects you've ever made or units you've ever produced on a logarithmic scale on your x-axis, and the cost on the marginal cost on a logarithmic scale on the y-axis gives a straight line. So there's a predictable pattern. We've seen it with solar panels have fallen at a steady rate since the 1970s. We've seen it with lithium-ion batteries. We saw it with the original Model T cars that Henry Ford produced. We see it in Wright's law was originally discovered by looking at how much it cost to produce airplanes in the 1920s and 30s, but it still holds true for airplanes made today, the F-35 fighter jet. So we see it in military technology. We see it in just every domain. This pattern of a new technology coming along, getting cheaper, but in this very predictable pattern. improving in performance, reaching some point where it starts to replace an old technology. And just as it's starting to, when it's like 3% market share, 5% market share, the old system reaches a peak and then starts to collapse. So Netflix replaces the video store, Blockbuster video store in the US, or the car starts to replace the horse. The number of horses in the US peaked when the number of cars was only something like 3 to 5% of the number of horses. So the number of horses reaches its peak, the number of cars is growing exponentially, and then the two cross each other in this sort of X-shaped pattern. And the whole thing plays out. The new technology rises in an S-shaped, sigmoidal curve that takes about 15 years or so. And like I said, I see it again and again and again. And every time we have some new technology that's 3 or 10 times cheaper, faster, better. So look back at the 100 Years' War. Starts out in Battle of Agincourt, 1415 in France. The English have longbowmen. 30 years later, the French are making cannons and fighting battles that it takes a day. They're at the start of the war, there are sieges that last for 6 months because we can't the English can't knock down the walls of French forts. By the end of the war, sieges are lasting a day because the cannon, is much more powerful than the trebuchet or than longbowmen. And that's in the 1400s. We see arrowheads. So I found this really interesting study of arrowheads from England from roughly 5,400 years ago, so 3,400 BC, where we see certain kinds of arrowheads and other kinds that are slightly older, those made before 3,400 BC, and those made after. And those two different styles are never found together in graves. So it seems like, there was a rapid transition from one to the other. We stopped making them one way and started making them the other way. And people have actually made reconstructions of these and tested them.
Brad.
Yes.
I just ask what? Could you describe? Maybe it's difficult, but what are the differences between the two styles?
Okay, so the old style is what's called pinnate or feather shaped. So it has a sharp point and kind of an oval shape, but with a sharp point. And the other is called a chisel style. So it's a triangular shape, but instead of having the point of the triangle face toward your, out of the arrow toward your prey, the sharp tip is buried into the shaft so that you have the flat edge of the triangle facing toward your prey. So with one kind of arrow, essentially just think of it as two triangles. And in one case, you're shooting the point of a triangle into your enemy, and the other, you're shooting the flat edge. And arrows, of course, spin as they fly. So if you shoot someone with a sharp tip, you poke a hole in them, basically. But the wound can close around the shaft of the arrow. If you're shooting someone with the flat edge of a triangle, you're essentially shooting them like with a razor blade, but it's a razor blade that's spinning. And they've actually done experiments with these two kinds of arrows, made modern reconstructions and shot them into ballistics gel, the kind of gel that the police use, for like testing what damage handguns might do or any projectile. They've shot these arrows into ballistics gel, and the wound made by the chisel shape, so the triangle where you're shooting the edge against your prey, is a much larger wound. And not only that, but the man who made these reconstruction arrows said that the more damaging arrow took about half as much time to make that arrowhead. It's just a simpler design, and it's easier to make. So it's so here we have a cheaper, better technology. It takes half as much effort to make, and it makes a much more damaging wound that is much more open and therefore will bleed more. So this is 5,400 years ago. So we see So we see in arrows, 5,400 years ago. We see in cannons replacing trebuchets, in firearms replacing crossbows, which themselves replaced bows and arrows, and not just military technology, but everything. We see it in cars replacing horses. We see it in tractors on farms replacing horses. We see it in the same sort of pattern in illegal activities. So one interesting example that I've looked into recently is in 2006, the United States government made it much more difficult to purchase pseudoephedrine, which is a chemical. It's used as in cough and cold medicines, but you can also put it into methamphetamine. So people were making, small batches. The Breaking Bad TV show was based on a chemistry teacher, making crystal meth. So the U.S. government made it much more difficult to purchase pseudoephedrine in large quantities. And pseudoephedrine comes from a plant called the ephedra plant. And when they banned the production of large scale purchasing of pseudoephedrine, gangs in Mexico figured out ways to make meth. We know other ways to synthesize it from standard household chemicals. So basically nail polish remover and paint thinner. So chemicals called toluene and acetone. So now instead of getting a chemical from a plant, a natural source, and then converting it into methamphetamine, they were creating methamphetamine from in any quantity they wanted, because they were using household chemicals that you can buy in large quantities. So the price of methamphetamine dropped. They started making methamphetamine, rather than small batches based on cough syrup purchased at a pharmacy. They were making very large batches, which brought the cost down dramatically. And now meth is an even larger problem than it was 15 years ago. And again, so we can, the Drug Enforcement Agency in the United States tests samples of confiscated meth and has published statistics on what percentage are made from ephedra and pseudoephedrine, so natural plant sources, and what percentage are synthesized from household chemicals, paint thinner, and nail polish remover, basically. And again, we see an S-shaped curve over a 15-year period, where this new technology, this new way of making the same product that's cheaper and faster and much more scalable, replaces the old one. And the result was, we now have meth on the streets that's much cheaper than it was 15 years ago. Kind of an example of a government law backfiring. And when the intention was to make it much more difficult to produce, to get your hands on the materials to make meth, they wound up actually making it much easier. So I've just been,
was this production method known before those new laws came into effect, and just it accelerated the adoption, or did this actually lead to the production of new knowledge of how to make meth in this alternative way?
It turns out that there are something like a dozen major ways of synthesizing methamphetamine, and it seems that the banning of pseudoephedrine caused the price to go up enough that there was investment. There was real investment. There was a new industry created here that's large scale, that uses large reactors. These are 1,000-liter stainless steel reactors located in warehouses that are near good shipping areas, so near a port or a train, railroad station or location where large amounts of chemicals can be moved in. Some of these synthesis methods are new, but also just logistics of this was also sort of new problems to be solved, because nobody had ever been making methamphetamines in that scale before. So there was a raid, and I believe it was 2016 or 17 in Mexico, where they confiscated something like 900 tons of methamphetamine, which is about $2 billion worth. And they just said, that's just physically impossible to produce that much product. When you are getting your raw materials from a pharmacy or from plants. So just the scale here was also sort of a new problem to be solved. So like I said, I'm collecting these examples, all throughout history of somebody coming up with a new way of doing things where, you see 900 tons of a product and 1,000-liter reactors seems crazy. Have $2 billion worth of a product all in one warehouse. But if you ask people, 20 years ago, if you told people, I took 100 photos today, and they were all basically the same. I took some selfies and I threw 99 of them away. People would say, "Oh, you're crazy. That must have cost a fortune." Or the idea here, I have a laptop with a webcam on it. I have a phone with a camera on the front and one on the back. I might have I've got two on the back actually. So I've got 3 cameras on my phone and one on my laptop. So I have 4 cameras, just right in arm's reach of me now. Whereas 20 years ago, if you told somebody I have 4 cameras, they'd say, "Wow, you must be a real photography buff," or whatever. If I travel and I bring my laptop and my phone with me, I'm bringing 4 cameras with me. But nobody 20 years ago carried 4 cameras with them unless they were a professional photographer. So we with new technologies we can produce larger volumes of things. It's not just we've replaced our old cameras with digital cameras, or old ways of old numbers of photos with the same number, just digital. By making things much cheaper and easier and faster, we open up whole new possibilities. People now have home security cameras that will record video essentially continuously. People have cameras on the dashboard of their car, so it's much easier to resolve insurance claims, because now half the people have a camera that's recording constantly. So it's not just a matter of one use gets replaced one for one, but when you have a steam powered ship, it will be 5 or 10 times physically larger than the sail powered ship. So products that did not make sense to move by ship when you had a sailing ship all of a sudden make sense because it's much cheaper when you have a coal-fired ship or a diesel-powered one or whatever else. Propeller planes to jet engines, where again, over about a 15-year period, a more powerful, more efficient engine results in a complete, not just replacement of propeller planes, but sort of rethinking of how airplane travel works. So with planes that fly faster, they also fly higher, so they're more efficient. So now an airline can be profitable just carrying people and their luggage, whereas with propeller planes, an airline really needed to have a postal contract, your government's contract to carry a certain amount of cargo, essentially, to make the line profitable. But if you have a jet plane, a jet can fly off to it rather than if you're moving packages and letters, you have to fly between major cities. But now with planes that are profitable just carrying passengers, you can rewrite the whole map of where planes fly. You can fly off to some tourist destination, just bringing families. Whereas with more expensive propeller planes, you bring businessmen and celebrities, people who could really afford and had a real need to travel. So you open up, the tourism industry. You open up, families traveling on a holiday as opposed to just business people traveling between 2 large cities. So you're not just changing, the economics and the volume, but you're also changing, which applications things are used for. When you have, digital photos are much cheaper, so you have the dash cam that you never had before, or flying it per kilometer per person becomes much cheaper. So you now have things like, holiday travel, flying somewhere for fun, as opposed to flying somewhere for business. So, yeah, that's what I've been doing. I mean, I can keep sort of rambling and giving examples, but like I said, I'm finding these examples in 4 or 5 basic areas of life that I keep looking at: energy, information, how we store and process information, how we get energy and what we use it for, food and medicine, the materials that we use, and transportation, how we move around. And it's the same pattern over and over again: predictably cheaper, better performance over time, resulting in S-shaped replacement of a old technology with a new one, all playing out over a 15-year or so pattern, or a period of time, and dramatically expanding the size of the market as the cost of moving people or goods, or getting a certain amount of energy, or processing a certain amount of information, storing a certain amount of information changes. And then, like I said, the interconnections between these.
Can I ask a question? I'm sort of curious.
Yes, please.
You talked about the difference between propeller planes and jet engines, and the role of government contracts there. I mean, the postal system itself is a kind of social coordination technology, I guess, but I don't know exactly where to draw the line between. I mean, I think it's fair to call certain forms of social organization, say like the limited liability corporation or stocks, or, I mean, these were very important parts of the first industrial revolution, for example. But I don't know whether they're technologies per se. I don't know how to, for example, make sense of something like Wright's law, what the axes would mean. But clearly they're involved in this web of technologies as kind of enabling factors. I mean, for example, you're in Norway, presumably you're doing remote work, as am I these days. Remote work as a social form of coordination is only possible because of certain technological advances, but it's clearly going to be a driving factor in the development of other ones. So how does one separate out technological disruption from like other forms of improvement in organization, or is that even necessary? Like, how do you, in your own mind, draw the line, like what is the proper scope for the kind of phenomena you're looking at?
Well, so far, I've been collecting a lot of these examples, and I want it to be as data-driven as possible. So this involves looking through, statistical abstracts that governments publish every year about how much steel was produced in the United States in 1 year by the electric arc furnace, by the oxygen blast furnace, or by the Siemens process, or something like that, or by the Bessemer process, or whatever. And seeing the patterns over time, and that's technological, but it's also, there's much more to it than that. There was the numbers that resulted in the amount of steel produced depended on laws that whatever the trade tariffs were, or imports or things. So I'm not really looking at pure sort of technological disruptions here, but there's also laws and government policies built into that. So I really haven't been kind of drawing the line. I'm using the word technology kind of loosely. I'm also, talking about sort of social disruptions, and I've been trying to find kind of sort of extreme. I'm looking at sort of what's the outer edges, of any given technology, or any sort of field of life. What's the sort of most extreme example of this? So to give an example, I've been looking at performance in sports over time, and what was the fastest runner in the Olympics. So looking through a lot of Olympic records, and seeing how they have changed over time, because we've seen things like in the high jump, for instance. So Dick Fosbury, 1968, the standard way of jumping over a bar in the Olympics, the high jump is a bar and a soft place to land. That's it. There's really no other equipment. So you run up to it and you jump over it. And the typical way was you'd run toward the bar and you'd jump over it forwards so that the bar would pass, your stomach would pass over the bar and you kick one leg up at the same time. And in 1968, Dick Fosbury did it the way that we do it now, which is run up and turn at the last second and go backwards over the bar, so that your stomach is, pointing up toward the sky. And it's called the Fosbury flop. And literally over the next 10 or 15 years, everybody who did it the old way sort of aged out of the sport, and everybody younger than him started learning it the new way. This complete turnover in, again, a 10 or 15 year period, where by 1980 or so, everybody is going over the bar backwards. So again, it's a replacement of an old way of doing things with a new way of doing things. And it takes about 15 years or so. So I started thinking, what's the
that's very
what is the
interesting.
simplest?
Sorry to interrupt you. Do you think?
Please do.
We have a saying in science, and I guess it's due to Fermi. Is that like that? People don't change their minds; they just die. Roughly speaking, I'm not sure that's Fermi.
Yeah.
Do you think the 15 years is kind of actually tied to like the length of an average career of a bureaucrat or a scientist or whatever? I mean, how important is this observation about human nature, that people get stuck in their ways and don't like to change their mind, and you need young people to come along and do it differently in order to have change? Do you think that's a significant part of the shape of these disruptions?
I don't know if it's an excellent question. I don't know if the sort of 15-year time frame is related to the age of lifespan of a career, for instance, because it's different for different technologies. So things like the black and white television in the U.S. went from less than 10% of households to more than 90% in about 5 years. Insulin is one of the fastest technologies ever adopted. It was just a year or two when we discovered that you can take insulin from the pancreases of animals and give it to people and control diabetes. So this is obviously one of the greatest discoveries. If you have diabetes, this is the difference between death and a manageable condition. So that was very rapidly adopted. And then other ones, are much slower. So I think a lot of the, what's happening is over the last decades, a lot of things are now computerized. So, digital cameras and computers and, computer chips that are in cars now. Cars are getting more electrified, and, so everything is becoming more like a computer. So I think a lot of this has to do with just the fact that, things that used to be done mechanically, like a slide rule, are now done digitally. So it's sort of how quickly computer technology can be made, how quickly printed circuit boards can be made into a plastic box and sold to people. So I don't really know, if it's related to the length of a career. But one thing that we have noticed is it's very often an outsider who sort of starts the new disruption. And so with the iPhone, Apple was a computer company. The name of the company was Apple Computers. They changed the name of the company to Apple Incorporated because of the success of products like the iPod and the iPhone, where Steve Jobs realized, this isn't, we're not really a computer company anymore. We're now we're also a phone company. So a number of companies could have made a flat, all glass, no keyboard phone. Could have made the iPhone. In 2007, Motorola was making phones, and BlackBerry and Nokia, and they didn't. They said a phone has 10, the number buttons on it, and people want a physical keyboard, and it has to have this little stem sticking out to let people know it has a powerful antenna. It's an outsider who is willing to rethink what a phone is. And one of Steve Jobs' quotes, he said, a phone doesn't need number keys on it. because people only use phones, 10% of the time for actually making a telephone call. If you have a mobile phone, you can just have the numbers pop up whenever you want to dial and then disappear from the screen when you don't need them. So you don't need, people want to see photos, they want to see video, they want to see, see the person you're talking to through a video conference. You don't want to see half your phone or more taken up by physical buttons. And it's very often outsiders, people who are not part of the sort of the mainstream industry. So Elon Musk is a great example. He was a computer programmer and was, I think, one of the founders of PayPal or key employee at PayPal, and started and found other engineers who said, we can make, if a lithium ion battery is powerful enough to power a laptop for 5 or 10 hours, then if we just strap 1,000 of these things together, we could move a car with it, and it would cost $100,000 because of the cost of the batteries at the time. So we have to make a sports car, and that's what they did. They made the Tesla Roadster, and then as the price of the lithium ion batteries came down, they went to a sort of high end, sort of no compromise car, the Tesla Model S, that competes with Mercedes or BMW. And then as the batteries got cheaper, now they're making cars that are more sort of mainstream. Everybody, the Model 3, more people can own it, and they're working apparently on cars that are even cheaper. They want to make cars that are the cheapest ones on the market and perform better. So here's somebody who is clearly not a auto executive or auto industry insider, had no real experience with car manufacturing, and is now the number one car manufacturer. Tesla is the biggest by market share. So yeah, I don't know if it's always younger people necessarily, but it is somebody from outside who is willing to sort of rethink basic rules and basic assumptions of what a phone is supposed to be, or what a camera is supposed to do, or what a car is supposed to be, or how it's supposed to work. And we do see that pattern, over and over again.
Yeah, sorry, I was just going to add very quickly. I think Dan, it certainly is an astute observation, and as Bradd said, it's an important question of what is this. What are the social and the psychological factors that are involved, if any, in the disruption time, the timing of that. So what is the there's some function presumably that determines the duration of disruption, like how long it takes, and presumably psychology at the individual and social level and other social factors must play a role in that. But it's an open question as to what those are. How could we operationalize those? How could we is there a research approach that could identify meaningful parameters or variables there that we could then try to analyze or even. I mean, it's a daunting challenge to try to figure out what the dynamics are that are really driving that, and I think it's an important question. But one more quick thing that is the way that we describe the one way that we define technology in this loose and general term is calling it practical knowledge, or knowledge that has sort of some agency, some causal power to it. A simpler way of saying that is that it's know-how, right? But that's a direct link from know-how to people embodying that knowledge in practice, right? I mean, if somebody has know-how, they know how to do something. Well, that's just how they do it, and people they get quite fixed in their ways. They get quite invested in how they're doing things, and to come along and change know-how is you can imagine that is obviously threatening and is it challenges status quo in various different ways, and so I think that there has to be some substantial role that's going on there in many of these disruptions. But Bradd did a great job of providing some counterexamples too, where perhaps that factor is overwhelmed by other things, like for example the need for the medication in the case of insulin, to be rolled out extremely rapidly, and so on. Yeah.
Yeah, I guess what I find the most interesting and I suppose controversial about the point of view you guys are advancing is when we talk about the history of these technologies, it's often from a thermodynamic point of view a kind of microscopic theory, right? It's kind of like this individual was an outsider and did this, and this thing happened which caused this person to realize that. Whereas, I mean, if it's true that there's this kind of more macroscopic view that holds for many different disruptions, those factors in a sense are they're decreased in importance. I mean, they clearly have to be there, but in some sense they're not well, I don't know how to put it exactly, but there must be something else going on, or in a sense those people, if they weren't happening to be there at that moment for that particular discovery, somebody else would have come along and done it. Now, one question I have is, you could clearly put the economy in that role of a driving force, right? It's kind of faceless, large-scale, distributed, and could pop up the people at the right time. And clearly that plays some role in, for example, the iPhone appearing when it did. I mean, when technologies converge, somebody's going to do it, and maybe it isn't the conservative mainstream people, but somehow if the demand is latent, somebody will find it. But are there earlier examples? I mean, maybe the Arrowhead one is such an example, but it's hard to tell because we don't have economic data for 5,000 years ago. Are there examples where maybe the economy doesn't play or isn't so obviously playing a role of being the obvious explanation for why the individual sort of microscopic factors might not be the complete story, like something large scale which you could point to and say, yeah, well, it makes sense that things would take the course they did as a result of interacting with that system. Maybe it's not a clear question, but
yeah, and just maybe just real quickly, let me preface this and then turn it over to Bradd. But before we got on the just before everybody else joined this session, Bradd was telling me about looking for examples and counterexamples that are not necessarily nested within the modern Western capital. I hesitate to use the word capitalism, but nested within our broad structure of global economics and trade. And there may be some very interesting examples outside of that paradigm that differ or that have differences or similarities that are revealing. And Bradd, maybe you can mention a couple of those. Those are really interesting examples. It might go a little bit of the way towards answering what Dan is asking here.
Yeah. So I think the drug example was a good one because the drug markups are so much that material cost is only sort of a portion of the product cost. A lot of the cost is just the risk of handling an illegal product. So in that one, economics plays a role, but it's not really the whole story. And in things like the arrow example, there still is economics. There's no money, but it's time and effort. So if one arrowhead takes half the time of the other and is more like foul prey, then that one is economically better. And for some of these, examples that I've looked at, there isn't, direct economics, but again, there's sort of implied economics here. So a mixture of copper and tin will melt at a lower temperature than either copper or tin individually. So when you make bronze, for instance, so if you have copper and tin in contact with each other and you start to heat them up, they melt at the point where the two are touching each other, and that becomes a liquid. And you can actually figure out how much energy it takes to melt bronze, a piece of bronze, compared to copper. And because the amount of energy lost goes up dramatically with the temperature, it's a very significant difference. I don't remember the figure off the top of my head, but it's economically much easier, however much fuel it would take or energy it would take. so, like I said, we've seen this in outside of capitalism, in the sort of modern, modern capitalism, because we've seen it in ancient examples from the Stone Age, from the Bronze Age. We've seen it in examples from communist societies as well. So in the 1920s, 30s, 40s, 50s, communist countries were adopting the tractor just like Western ones were. And we see similar behavior patterns. So the Soviets in the 1950s were building up a nuclear arsenal, just like the Western countries were. And we see the same sort of pattern of behavior. We see it in military technologies. We see it in, we see the like I said, the same sort of pattern of number of hours it takes to assemble an F-35 fighter jet, going down as the cumulative number of jets ever built goes up. So it's it's sort of a hardwired mechanism. This pattern of disruption is kind of hardwired into how not just people behave, but we've seen it in animals as well. So in the middle of the 1900s, birds in the UK discovered that they could peck through the foil lids on top of milk bottles and drink the cream from the milk. And this was first observed in one town in the UK, and then it spread over about a 20-year period, throughout all of England and maybe parts of Scotland, but at least throughout all of England. So birds, learned from each other that, hey, you can get food just by pecking through this. And we got the same sort of growth in popularity over time, of this new technology, this new idea that spread through this social network of birds, watching each other and then flying somewhere else and teaching other birds, either intentionally or just other birds watching them, teaching them. So this is not a behavior pattern that's restricted to even humans. So it seems to be a phenomenon of that's driven by economics in terms of benefit and cost. So obviously, pecking through a foil lid to get to cream on milk has a great benefit and little cost. So this is something that is ripe to spread quickly. It's not restricted to sort of high tech Silicon Valley, new technologies, iPhones and Tesla cars, but it's also to military technologies. It's to military technologies in history. It's to it's found in capitalist societies, communist ones, and it seems to be the same sort of pattern over and over again. New technology gets better in performance, gets cheaper in this predictable pattern, reaches a crossing point and rapidly gets adopted in a sigmoidal process. We're seeing it in the Omicron variant, where this rapid uptake of something that spreads 4 times faster than the Delta variant, all of a sudden is now taking over the marketplace of So we see it in how epidemics, pandemics. We see it in bacterial growth, and we see it in human behavior as well.
How would you distinguish those examples? I guess one concern I have about a potential theoretical explanation for these observations is if indeed these evolutionary processes are the same process, then it's in some sense a very generic observation, right? So I would see the analogy between. I mean, I'm interested in you if you disagree, but I would see the analogy between technological disruption and, say, the out-competition of Omicron, of the Delta variant, as actually a little discouraging from the point of view of trying to use the ideas around technological disruption to predict anything or understand what is going on. Do you agree or disagree that, would you really strongly say they're exactly the same kind of phenomena? Is that the scope at which you want to understand these patterns, or is that just a kind of analogy?
I think in that case, it's an analogy. So we see, I'm not trying to claim that, this is the one mechanism that governs all human behavior. But at the same time, I've collected enough examples now, and maybe, I'm cherry picking. Maybe I'm looking for examples that fit the pattern, and, I'm not really that interested in the ones that don't. I'm also looking at ones where I can collect data. So that means looking through, like I said, statistical abstracts to come up with the amount of copper produced by year, or the length of roads in the U.S. highway system, or the number of, the length of railroads in the European railway system, or length of canals before that, or the length of telephone wires, or things. But I've seen enough of these, and they have so many similarities, especially when it's one technology replacing another. So I put less effort into some of the social ones of democracy replacing authoritarianism, or things, and how quickly that plays out. And I know that there are social scientists who look at those, how revolutions happen when tipping points are reached and a certain portion of the population supports a new idea. This is Thomas Kuhn's structure of scientific revolutions. It was based on this idea of a new paradigm replacing an old one. So, I mean, I'm not claiming that everything I'm doing is entirely unique. I'm collecting examples, and I'm particularly interested in the technological examples that have, some economic and, adoption or production level data behind them, that I can produce graphs over time and see enough of this pattern that if you see a pattern enough times, then hopefully the idea is that when you see some new technology come along, you can identify that, yes, this feels like it's it's like the technologies that we've seen before. This is a technology that could be very disruptive, because I've seen enough historical examples of this, that I'm seeing costs going down over time, performance getting better, a clearly disruptable some sort of 10x performance difference, an old way of doing things that is ripe for disruption. So I'm not trying to make some sort of formal scientific theory. I'm collecting enough examples, and it's been sort of eerie enough to see enough of these that have sort of the same story play out over time, where red fabric dyes, alizarin dye, was made in the 1880s, where we were able to synthesize dyes that we found in nature. So we don't have to grow plants like the madder plant, which contains rose madder, the red the red dye for fabrics. And it gets cheaper. It's 10 times cheaper. It winds up replacing natural red dyes. And then 10 years later, the exact same story happens again with indigo, where now we can synthesize blue dyes. And it's baffling as to why didn't people see this happening? Well, or maybe they did, but they couldn't do anything about it. But dyes that we got from nature that were red in color, we wound up synthesizing same chemicals. So we're able to produce them in large volumes. And then 10 years later, we are able to synthesize blue dyes that we got from nature. And then 110 years later, the US government passes a law that says, let's make pseudoephedrine much more difficult to access. And maybe if lawmakers knew about these examples of red dyes and purple dyes, they would have thought twice, or done some sort of modeling or simulation or analysis driven by previous experience, previous data, driven by analogy, driven by knowledge of previous examples, that said, if we pass this law, we're creating a situation where someone will come along and artificially synthesize methamphetamines rather than making them from natural sources, and could potentially make this situation 10 times worse, which is exactly the situation we're in now.
I think it's a great, in some sense, a great problem to have. So the beginning of this seminar series, we sort of started out with this question: can and should technology disruption be a science? Does it justify its own subdiscipline? And in some ways, it would be like you said, Dan. If I'm understanding you correctly, there is a sense in which it might be discouraging to find out that there is the basis of the phenomena is simple enough that it doesn't really merit the status of a domain, a scientific domain of inquiry. That it's just there isn't enough there to justify that. But on the other hand,
let me clarify then. So I think the examples Bradd presented and the other things you've told me about, I mean, it seems convincing that there is something there, but there's very general phenomena in systems and nonlinear dynamical systems, as both of you know very well, phase transitions and critical points and all of that. And no doubt that all applies. It's just it's a question of, like, well, what universality class are these phase transitions? Something like that. So I'm not sort of saying that. So once you accept that, yes, there's a broader setting in which both biological evolution and many other phenomena and technological disruption sit, that seems reasonable to me. I'm asking a secondary question, which is, well, how do you distinguish, I mean, things like these 15 years or the 75% inflection point on the vertical axis that you've talked about, Adam? These kinds of examples of distinguishing characteristics of these phase transitions are what seem interesting to me. I want to sort of hear more about, and maybe in future sessions, those phenomena which help to disentangle these phase transitions from just, I mean, a generic one, which, we know there's plenty of such phenomena in nature. So observing that it's one of those phenomena is interesting and already, I think, news to a lot of people, including people with decision-making power. But scientifically, what I find particularly interesting is, once you grant that, what further can be said specifically about this class of phase transitions? Does that make sense?
Yeah, that makes very good sense. And I think you may be, it's possible you may be being generous and making the assumption that there are a sufficient number of distinguishing features to make this special, a special class or case of a more general phenomena that is worthy of a fully scientific level of inquiry, as opposed to maybe something a little more practical, like what we do at Rethink X, which is to take this insight, draw what we can from it, and then try to make that information and knowledge useful, that insight useful to various actors and institutions around the world. And I think those projects dovetail, but I agree certainly, and I don't want to speak for you, Bradd, so I'm interested to hear what you say as well. But from my perspective, I do agree, Dan, that scientifically, the things that are most interesting are the things that set this particular set of sigmoidal dynamics apart from other examples of that we see in nature. And I remain optimistic that there are enough things about technology disruption that do make it different and that would be worthy of study. But we could be wrong. We have to go into this not assuming that all of that detail is going to be interesting and it's worth taking the time to discover. Right? It could be that it's all just not. It's certainly possible. It could be just not that different from epidemiological sigmoid curves, and it's just that we're not going to find much else there that distinguishes it. So it's possible both of those things are true. I hope that I'm wrong about and that it's more exciting rather than dismal. But we should be open-minded and not not presume, I think, that we're going to find something very, very different and exciting in this particular case. It could be that it's just another species of the larger population of phenomena that are like this. So, Ed, you have any thoughts?
Yeah, I think my big concern over the past year or so here is just compiling examples because I'm interested in this phenomenon. And if I've been sort of making graphs of what percentage of people got insulin and what the price was and how many what percentage of steel was made by different processes. And I haven't been doing sort of any sort of theoretical modeling behind it. I know that there are plenty of cases that people have in the past of A to B to C transition. So sort of in epidemiology, there are the SIR models, susceptible, infected, and recovered, and a lot of those ideas have been applied to technology adoption, diffusion of innovations for decades now. So Everett Rogers, back in the 60s, and so was looking at and talking explicitly to George Bass's model of the Bass diffusion model, it's called, where non-adopters of a technology become adopters, and there's sort of spontaneous conversion. So each time unit, some fraction of the non-adopters become adopters, and then there's another that is people get recruited. So that's a factor that depends on the number of adopters multiplied by the number of non-adopters. So those two mechanisms, you add them together, and that's the rate of adoption. And then we try to use historical examples to gauge the values of those parameters. So there's enough of this work that's been done of comparing fads to epidemics, or comparing adoption of a new technology to and diffusion of an innovation to getting sort of infected with an idea. There are enough cases where we've seen it in in technologies, we've seen it in political ideas, we've seen it in religions of the rate at which adoption of a religion in a particular area follows kind of an S-shaped curve. So I haven't really been very much focused on the theory behind it, or even any sort of attempt at modeling. What I've been doing so far is just sort of more descriptive, collecting the examples, and then seeing what things they have in common, what constitutes a pattern to technological disruption, as opposed to sort of trying to explain the behaviors.
Now, I should add in here, just for context, that we do use a theoretical theoretical framework. And this is the one that Tony Seba developed. But it's not, and Tony's is itself a sort of a meta theory. It's well, not a meta theory, but it's an amalgam of several other pieces of theoretical work that have been done previously. So it draws from Clayton Christensen, for example, and that's explicit. It's cited right on all of his in all of the material. But this theory is very far from complete, and I think one of the projects for one of my hopes for this project in this seminar is to think a little more clearly about what would a theory technological disruption look like, and can we build on what we've got? And we are using a theory at the moment, but it has serious limitations, and it's narrow. It's focused only on a certain type of technology disruption, and wouldn't extend to, for example, to many of the historical instances that Bradd has talked about, because the pieces are not necessarily there. So this is part of the larger project here of thinking, is there a science to be had here? And for any science, at least to my thinking, you do need some sort of theory, some sort of theoretical framework that provides the basis for explanation, and you need a body of empirical evidence. And I think we are seeing the beginnings of those things emerge. The question is there enough, and is there enough consistency within the material that we have that it looks like there's something of real interest here? So I guess that continues to be the open question that challenges us in this seminar, and then I suppose to some extent it factors into our work as well, Brad. I mean, it's part of what we think about a little bit on our team, although we're less academic, of course, as you can imagine, than we are practical, trying to provide useful insight to decision makers of various kinds. But I remain hopeful that there is a set of relatively elegant and parsimonious explanations for this phenomena, which seems interesting, and that the phenomena itself is consistent enough that we can hope to understand the past and then also make some meaningful predictions about the future as well. But we have a long way to go. We're certainly not there yet, but it's extremely important work, I think, that Brad has done already on the compiling evidence side of things. It's amazing work, and some of the examples are incredible. And Brad's only scratched the surface here. There are literally dozens and dozens more that he hasn't mentioned that are really interesting. So I guess with that, I want to say thanks, Brad, for joining us. It was really, really great to have you.
Oh, thank you.
Okay, so we'll leave it at that for this session. I'm going to take a brief break to pause the recording, and then we'll move on to the coding part of today's agenda. So we'll maybe take a 5-minute break. What's the time now? It's 12:13 here, so at about 19 past, we'll start the coding. Right, so Adam and Brad, Adam, I'll see you next week. Brad, I hope you can come back and speak again at some point. If not, then I look forward to seeing your book.
Great, thank you,
Okay,
guys.
thank you.
Take care. Bye, everybody.
Thanks.